Efacec is the largest Portuguese company in the electromechanical industry sector. The Efacec Transportation Business Unit operates in the segments of railways, light rails and highways. The vertical motivation of the transportation pilot is to use 5G communications to support railway signalling operations, to meet railway level crossing communication requirements as a machine-to-machine perspective. Moreover, the pilot is based in 2 use cases, and the main purposes are to demonstrate the capability of the 5G technology, supported by the 5Growth platform, to enable fixed permanent 5G critical communications between train approaching detectors and level crossing controllers over a secure network and keeping a low end-to-end latency between devices, reducing by using wireless technology the capex, the cable and installation costs. The second use case aims to enable high-definition video transmission from level crossing surveillance cameras to approaching trains and maintenance agent tablet devices by establishing communication on demand over a secure network and keeping a low end-to-end latency between devices and high-throughput data communication, reinforcing this way the safety conditions of the level crossing area. For the transportation pilot, a fully functional 5G standalone network is available, encompassing a 5G core and a 5G radio access network RAN with the following components: centralized unit CU, distributed unit DU and radio unit RU. The 5G core is installed at IT Aveiro Building 1, CU plus DU at IT Aveiro Building 2, and the RU is deployed on top of a water tower at Aveiro Harbour, 7 kilometers away from IT Building 2 in the vertical pilot deployment scenario. The radio access network component is based on ASOC's Cyrus 2.0. ASOC provides a fully virtualized RAN solution, delivering standalone 5G cellular connectivity. It is fully virtualized across all layers and follows the Open RAN architecture, an open standard that decomposes the 3GPP G-Node B into 3 different components: the RU, radio unit, the DU, distributed unit, and the CU, centralized unit. The decoupling of these components is one of the differentiating features of the Aveiro 5G pilots. The CU and the DU can be deployed in different locations or can be co-located. The radio unit is in charge of converting radio signals into a digital stream for transmission over packet networks. Concerning the user equipment, UE, multiple devices have been used, including Huawei 5G CPE Pro 1 and Pro 2 and Quectel RM500Q-GL. The different components of the radio access network can be managed and monitored to guarantee optimal performance. The 5G core is based on Fraunhofer Focus Open 5G Core. Open 5G core components, including all the fundamental 3GPP 5G core network functions, can be deployed as containers or virtual machines. Open 5G core follows the service-based architecture, in which self-contained, independent and reusable network functions expose their functionality through a well-defined REST interface. O5GC command line interface enables configuration and monitoring of all 5G core components, including the AMF, SMF, UPF, PCF and RF. The integration of 5Growth with 5G VINI involves the adaptation of the 5GRVS requests to the Sonata Slice Manager. The flow between 5GRVS and the 5G VINI's Network Function Virtualization Orchestrator (NFVO) follows the 3GPP standard TS28.531. 5Growth is used at the vertical side to map the use case service to an end-to-end slice request to the 5G VINI platform to provision the 5G service, including all the 5G core functions and related connections and configurations to the ASOC's 5G RAN. This integration has allowed the availability of the interdomain and security innovations led by IT Aveiro and also supported in Sonata through extensions implemented on it. The interdomain innovation in 5Growth allows the verticals to instantiate vertical functions in different network operator domains, interswitching them as a single multi-operator interdomain network service. The vertical can then use resources and assets that are under the coverage of different operators without the need for operator mediation. The security innovation introduces the moving target defense mechanism, where the service listening port is constantly mutating in a synchronized way with the client. As a result, attackers surveying for open ports will obtain outdated information, reducing attack capability. Both innovations can be combined for interdomain network slicing with advanced security capabilities. The 5G VINI monitoring platform was integrated with the 5Growth monitoring platform using the Semantic Data Aggregator (SDA). The probes are located in the pilot UEs or servers and periodically send data metrics, latency, jitter, packet loss, and average throughput to the 5G VINI monitoring platform. The 5Growth monitoring displays the collected metrics in visual form with Grafana subcomponent. The first use case implements the level crossing control over 5G communication and has a complete system distributed in 3 different locations. The level crossing controller that receives information from remote railway sensors and manages the safety operations regarding bells, traffic lights, and usually physical barriers. And 2 remote signaling cabinets to detect the presence of a train and communicate wirelessly using 5G technology the information of the track status to the level crossing controller cabinet. All information from remote cabinets is exchanged to the central unit using safety and security protocols in order to provide secure communications to the system. The level crossing system cabinets are based on the following equipment. Frauscher equipment that manages the electrical signal received from the sensor and communicates via FSE Ethernet protocol, Efacec 5G CPE, and a robust external antenna to allow 5G communication between the remote cabinets and the level crossing controller. Both remote cabinets are power supplied via solar panel system, eliminating cable and conducts costs between the level crossing and the remote cabinets. The level crossing central cabinet receives data from the remote cabinets and manages the signaling operations procedures, assuring the safety conditions for people, cars and trains. For strike-in purposes, both remote cabinets are connected to Frauscher wheel sensor that detects a train approaching the level crossing. The wheel sensor is a magnetic unit that translates the magnetic changes to an electrical signal. This electrical signal is then received and processed in the remote cabinet, allowing to calculate the number of axles passing through the sensor, speed train, wheel diameter, etc. This information is then communicated to the central cabinet controller via 5G communication using a CPE 5G equipment developed by Efacec, using a FSE protocol over a secure channel tunnel. The information sent by both remote cabinets are recaptioned in the central control cabinet using another 5G CPE equipment that has the secure channel tunnel endpoint. This information is then fed to HEMA PLC that controls the level crossing status by operating the signaling equipment that is in the level crossing on both sides of the road. The white light of the traffic road means that the level crossing is free to cars. The 2 red lights flashing intermittently means that the train is approaching the level crossing and cars cannot cross the road. While the train is on the level crossing, both bells are ringing, reinforcing the safety conditions of the system. The final validation campaign was carried out using 2 different 5G radio access networks, an experimental Open RAN and a carrier-grade 5G standalone network of the 5Gainer project implemented in the same site. The performance evaluation of Open RAN has the following results in terms of end-to-end round-trip time and latency through secure VPN encrypted tunnel. The average value of end-to-end latency is 30 milliseconds. The minimum value is 20 milliseconds and the maximum value is 48 milliseconds. The jitter value measured was 4.7 milliseconds. Under the same solution, the end-to-end throughput with secure VPN using UDP protocol is 15.9 megabits per second. The performance evaluation of the 5Gainer has the following results in terms of end-to-end round-trip time and latency through secure VPN encrypted tunnel. The average value of end-to-end latency is 10 milliseconds. The minimum value is 7 milliseconds and the maximum value is 21 milliseconds. The jitter value measured was 1.8 milliseconds. Under the same 5G SA5 gainer, the end-to-end throughput with secure VPN and using UDP protocol is 92.5 megabits per second. The use case 2 is based on GPS location, and when the train approaches a configurable distance of the level crossing, the video of the level crossing is transmitted using 5G technology to the driver console, allowing the driver to verify the safety conditions of the level crossing area. The architecture of use case 2 is based on the following scheme. The Bosch camera installed in the level crossing pole directly connected to the 5G router that, in combination with a Raspberry Pi, is used to establish a secure WireGuard tunnel for the video streaming. In the train cabin, the driver has a SysLogic console directly connected to another 5G router. The level crossing video camera is installed at the top of the pole and allows to have a big aerial observation that includes track line and traffic road in both ways. A Huawei 5G router and Raspberry Pi for secure communications are installed inside the level crossing communication cabinet and are responsible to communicate with the train equipment. Inside the train driver's cabin, a SysLogic console and a Huawei 5G router are installed. An Efacec application is running on the driver console using Debian Linux distribution, which automatically displays the video stream to the driver as soon as it passes the pre-configured trigger points using GPS geolocation. These graphs and tables show the performance of the Open RAN network regarding latency, jitter and packet loss. Tests were also performed by passing traffic through the WireGuard secure tunnel. On the left, it is shown the round-trip time histogram. In the tables, we can see that the average latency obtained was 19.5 milliseconds, with a jitter of 3.4 milliseconds, and the packet loss in this network is more significant at 32 megabits per second. These graphs and tables show the performance of the 5-gainer network regarding latency, jitter, and packet loss. The tests were also performed by passing traffic through the WireGuard secure tunnel. On the left, it is shown the end-to-end round-trip time histogram. In the tables, we can see that the average end-to-end latency obtained was 14 milliseconds, with jitter of 2.5 milliseconds, and the packet loss is only relevant at 80 megabits per second. The following videos illustrate the relevant functional details of both use cases. Please note that when the train, in video 3, is far from the level crossing, the video 1 shows that, the level crossing control equipment shows that the axles counter is 0. In video 2, the synoptic shows the real-time representation of the level crossing, and video 4 also shows the white traffic lights are on. Related to the use case 2, when the train is far away from the level crossing, like video 5 and 3 show, the driver's console exhibits a GPS map indicating the train location. When the train passes over the train detector, you can see in video 1, it is shown the axles counter incrementation and the red traffic lights start to flash in videos 2 and 4, as well as the bells start ringing. Related to the use case 2, when the train approaches the level crossing, the video streaming is triggered into the driver's console, like shown in video 5 and 6. When the train is detected in the remote wheel sensor, it means that it is leaving the level crossing area, and in video 1, the axle counter equipment is decreasing to 0, meaning that the level crossing area is released. In this moment, the level crossing is free and road traffic can cross the railway track. In that situation, the video 2 and 4, red traffic lights stop flashing and start showing the white traffic lights to the road traffic. Notice that also the bells stop ringing. Related to the use case 2, when the train leaves the level crossing area, the video streaming stops to be shown to the driver and the GPS location map is exhibited. As a conclusion, we may consider that the business, functional and technical needs of Efacec S regarding safety and security of a level crossing have been introduced, along with the solution concept principles implemented in 5Growth project. The 5G infrastructure required to execute and validate this pilot was deployed, configured and integrated with level crossing Efacec's relevant components at Aveiro Harbour. The pilot's infrastructure allowed the integration and validation of 5Growth innovations and their interaction with 5G VINI, supported by the 5Growth stack. The functional requirements, as well as the performance of the end-to-end service in terms of latency and data rate KPIs, has been real-time monitored, analysed and validated. Thank you all for your attention. This is the most relevant information regarding the status of the vertical transportation pilot related to month 30.